We are now define the angular momentum of a particle or a system of particles. Let's first start with the definition of the angular momentum of a particle. If we have a particle, for example, this particle, which move with the velocity v and have the momentum p, and we will define the angular momentum of this particle around the point O, or we may say the angular momentum around the axis that pass the point O. This by this equation, L is equal to R cross P. Here, R is the position vector of this particle from the point O. Okay, so from this figure, you can see that this is the position vector R and this is the momentum vector P of this particle. The cross product of R and P, or R cross P, is L, which has the direction point upward in the C direction like this. Okay, that follows from the definition of the cross product or the vector product, and also from the definition of the vector product, you can see that the magnitude of the angular momentum L is equal to mvr times phi. Here, phi is the angle between the position vector and the momentum. R is the magnitude of the position vector, and mv here is the magnitude of the momentum p. We have p equal to mv. So this is the magnitude of p. So this is the magnitude of the angular momentum. Now, we have the definition of the angular momentum. We will discuss next the relation between the angular momentum and the torque. Okay. From the definition of the torque, we have that the net torque on the particle is equal to the R cross the net force. Okay, this is the net force on the particle. This is the position vector point from O to the particle. So we have that torque is equal to R cross F, which we know that from the second law of Newton, the Newton's second law of motion, the force acting on a particle is equal to the rate of change of the linear momentum of the particle. So we replace the net force with dp by dt. So we have the net torque on a particle is equal to R cross dp by dt. Now, we can rewrite this equation to be this form by adding the second term R dr by dt cos p. Okay, we can do this. It is because by definition also we know that dr by dt is equal to v, or the velocity of the particle, and we also have p is equal to mv. So dr by dt cross p is equal to the v cross mv. But v, the velocity vector, and mv, the momentum vector, must have the same, must point in the same direction, because m is a scalar. So m times v point in the same direction as v. So from the definition of cross product or the vector product, the vector that parallel, the vector product of two vectors, those are parallel, is equal to 0. So it means that this term is 0. So we add 0 to this term and it changes nothing. So we can add this term to this term to get this equation. But the reason that we add this term, because we can rearrange this term to be d by dt of r cross p, right? This is from the definition of the derivative of the vector product. So we have that r cross dp by dt plus dr by dt cross p is equal to the d by dt of r cross p. But from the definition of angular momentum, you can see that r cross p is L. So we have that this is dl by dt, which means that we can relate the net torque on a particle with the rate of change of the angular momentum. This relation is very similar to the second law if we write the force or the net force in terms of the rate of change of the linear momentum. Okay, so you can see the similarity between these two equations. Okay, before we go further, let me remind you that from the definition of angular momentum, we can have the angular momentum for a particle even the particle move in a straight line. The definition of the angular momentum do nothing with the rotation. Okay, even though we define some axis, but it's not necessary that the particle have to rotate about this axis. Even the particle moving in a straight line, we can define the angular momentum. Anyway, the important application of the angular momentum always related to the rotation problem. So, in this for the basic physics, most of the problem is related to the rotation somehow. Anyway, in general, it's not necessary that the angular momentum have to it's not necessary that a particle have to rotate about an axis to have angular momentum. Okay. Now, let us move to the case of the system of particles. Okay. The system of particles. Now, if we have more than one particle, we can define the total angular momentum allow a point, for example, the point O as in this figure. But now we have more than one particle. We can define the total angular momentum to be the summation of the angular momentum of each particle. Okay, so this is the definition of the angular momentum of a system of particles. Again, it is easy to show that the angular momentum is related to the torque in the same way. The angular momentum of a system of particles is related to the torque in the same way as the angular momentum of a single particle. This is quite simple because from the definition here, and if I do the time derivative of the total angular momentum, we can write it as a summation of the time derivative of the angular momentum of each particle. So this is a summation here. But the rate of change or the time derivative of the angular momentum of each particle is equal to the torque act on that particle. So the summation of the rate of change of the angular momentum is equal to the summation of the torque, and we can say that this is the torque on the system, the total torque. The total torque on the system is a summation of the torque on each particle. So we have this relation that the total torque on the system is equal to the rate of change of the total angular momentum of the system. Anyway, we have one thing that is very similar to the case of linear momentum. That is, the total torque here is the torque from the external force only. The external force here means it is not the force between the particle in the system. It comes from outside the system. It comes from outside the system of the particle. So we count only the torque from the external force only to change the total angular momentum. We can prove that the torque from the internal force is 0. Okay, this is simple. Let's see if we have two particles, particle number 1 and the particle number 2, and if we define the point O here, so we have the position vector R1 and the position vector R2. And if we look at the internal force between these two particles, so we have F12, the force on the okay, just use the notation F21. The force from the force on the particle number 1 from the particle number 2, or the force from the particle number 2 to the particle number 1. And we also have F12, the force from particle number 1 to the particle number 2. From the third law, the Newton's third law, this is the force, the mutual force between the particle 1 and 2. It means that we have F21 equal to minus of F12. So if we want to calculate the net torque on the system, we have that the net torque is the torque on the particle number 1 plus the torque on the particle number 2, which equal to R1 plus F1 F21 plus R2 plus F12. But from this relation, we must have that this equals to the R1 minus R2 of cross F21. Okay, we use the distributive property of the cross product together with the third law. Anyway, you can see that R1 minus R2 is this vector. This is R1 minus R2. and R1 minus R2 point in the same direction as F21, right? So it means that R1 minus R2 parallel to F21. So we have the cross product of two vectors. Those are parallel. The result is, of course, equal to 0. Which means that if we look at the pair of action-reaction force and we calculate the total torque from those two action and reaction pair, those action and reaction pair, we will have that for each pair, the net torque for each pair is equal to 0. So when we sum up all pairs in the system, we will have that the net torque for the internal force is equal to 0, which means that when we talk about the rate of change of the angular momentum here, it must be equal to the total torque from the external force only, because the internal part, the torque from the internal part, when we sum up in this equation, will equal to 0. So we will have only the torque from the external force only to change the angular momentum.